Question number 14 then is another magnetism question. This one talks about setting up a flux field in a wooden ring. Now remember, normally we're considering magnetic circuits, and so we might think that wood not very magnetic. And so that I guess leads us to believe that a small current such as 5 amps would produce a relatively weak magnetic field in a piece of wood. Okay, so then let's think about the magnetic circuit. And so we have a wooden ring, and maybe this would represent the wooden ring. Okay, so we are given the average diameter of the ring, and what that typically means is that the average diameter will be represented by the dashed line, and therefore the length of the magnetic circuit would be the length of the dashed line, or the circumference of a circle, represented by a diameter of 0.2 meters, I guess, right? So the length then will be the circumference of the circle, or pi times its diameter, and so we can say 0.2 times pi, and a unit being meters, I guess. In addition, let's think about the cross-sectional area here. We have the area given as 400 millimeters squared, and remember that we must use the base unit of meters squared, and so convert millimeters squared to meters squared by multiplying by 1 meter over 1,000 millimeters, and again by 1 meter over 1,000 millimeters. Now, if we do that, remember that the unit of millimeters here cancels with the unit of millimeters here cancels with the unit of millimeters, and we're left with meters times meters, which will give us meters squared. And so to do our conversion, remember that 1,000 is 10 to the 3, and we have it twice. If it's in the denominator, as that goes to the numerator, we have 10 to the negative 3 multiplied by 10 to the negative 3. And so that gives us an area of 400 times 10 to the negative 6 meters squared. Now we could write that as 4 times 10 to the negative 4 meters squared, but we'll go ahead and leave it as 10 to the negative 6, or micrometers squared, I guess, if you would. Now, the other thing then I guess we'll consider here is, let us think a moment about our, let's go back to thinking about our magnetic circuit. Now this piece of wood here, we're told, is wound with a coil of wire which consists of 300 turns, and as we run a current through that piece of wire, we're going to set up a flux field, or a magnetic field, in the piece of wood, I suppose. And so the last thing I guess that we'll consider now is that our number of turns, or number of loops, then being 300 turns. Okay, so in order for us then to go ahead now and calculate the flux, we'll start off by saying that we need to calculate the magnetomotive force, or MMF, of the circuit, and that will be equal to the number of turns multiplied by the current. So we have 300 turns multiplied by 5 amps, and that results in 1,500 amp turns as the MMF. We also want to calculate the reluctance of the circuit. Now, the reluctance can be given by the length of the circuit divided by mu naught times the area, where, remember, the length we have calculated as 0.2 times pi meters. mu naught is the permeability of free space, and it is 4 pi times 10 to the negative 7 henries per meter. And we multiply that by the area, which we determined was 400 times 10 to the negative 6 meters squared. Now here we have meters cancels with one of these meters, meters cancels with meters, and the unit that we're left with is like 1 over a Henry, which we should be able to show is equivalent to the unit of reluctance, which is amp turns per Weber. Now, we can also show here, I guess, that pi cancels with pi, so we can eliminate pi from the calculation. That will reduce the error somewhat. And so then we can calculate the reluctance as 0.2 divided by 4 times 10 to the negative 7, and also divided by 400 times 10 to the negative 6. Our reluctance then will come out to be 1.25 times 10 to the 9 amp turns per Weber. Now we note that 10 to the 9 here is just a very large number, and so the idea, remember, is that wood is not very magnetic, and it's basically the same as setting up a magnetic field in the air, and so that gives us a very high reluctance to the production of flux, meaning it's very difficult to produce a magnetic field in a piece of wood. Okay, and so a very high number for the reluctance. Now, magnetic circuit Ohm's law then suggests that the flux produced will be equal to the MMF that produces the flux divided by the reluctance of the circuit to have a magnetic field produced in it. And so the magnetomotive force we calculated above as 1500 amp turns, and we'll divide that now by 1.25 times 10 to the 9 amp turns per Weber. And I guess here amp turns cancels with amp turns, leaves us with 1 over Webers in the denominator, which gives us a unit of Webers for flux. If we do the math, 1500 divided by 1.25 times 10 to the 9 gives us a flux of 1.2 times 10 to the negative 6 Webers, or the flux produced is 1.2 micro Webers, whereby remember that the metric prefix micro stands for 10 to the negative 6.